Alright, here we're going to be learning about proving congruent triangles. So we've learned about some of the theorems that we're going to be using for this unit. We've learned about angle, side, angle, 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 side, side, angle, side, 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 and hypotenuse, leg. So these are all going to be really useful in proving that triangles are congruent. Actually, these are pretty much going to be our final step in showing that two triangles are the same. But to get to that point, we first need to show that these parts are going to be the same. So we're going to need to show that we have congruent angles and sides, and then make sure that we have all the parts necessary to use one of these theorems. Before we get to that, we have to learn about three new definitions, although they're not really new. We've actually talked about each of them. I'm just going to define them so that we can use them in a proof. First one is the definition of an angle bisector. A line is an angle bisector if and only if it divides an angle into two congruent angles. So it's going to split an angle directly in half. So AOB is split directly in half by this line PO. So we can say that PO bisects angle AOB. This angle and this angle are the same because that angle is getting split directly in half, forming two congruent angles. We could also say that AOB is bisected by line PO. A segment bisector is really similar. It's a line, and it's a segment bisector if and only if it divides a segment into two congruent segments. So instead of splitting an angle, we're splitting a line. So CD is the bisector, or bisects AB, because it forms two congruent angles, two congruent segments on either side. That side, this segment and this segment are the same. That's why they're marked as congruent. So we're going to do two practice problems with those two. DB bisects angle ABC. ABC. What's the value of x? So if that's bisected, that means that and that are going to be the same. So I could say that 3x minus 7 equals 20. And now I want to solve that equation. I'm going to add 7 to both sides. That would give me 3x equals 27, and then divide by 3 on both sides to get that x is just 9. That's the number that would make these two angles congruent, or really make that angle equal to 20. For number 2, LM, that line bisects line PQ. So these are congruent. So my equation is that 4x plus 3 equals 6x minus 12. Those are two congruent segments, so I can set them equal to each other. Then I'm going to solve. I'm going to add 12 to both sides and subtract 4x from both sides. I'm not really going to show that step, but I'm going to add the 12 over and get 15, and subtract the 4x from both sides and get 2x, and then divide by 2. And so x equals 7.5. That is the value of x that makes these two expressions equal to each other. We've actually calculated midpoints before. Now we're just going to define them. The definition of a midpoint is a point. It is a midpoint if and only if it divides a segment into two congruent segments. That should sound really familiar because it's the exact same thing as a segment bisector, except it's a point. Instead of being a line, it's a point, but it's still splitting it into two congruent segments. So in this case, point M is the midpoint of segment AB. Alright, now we're going to do some problems using those in a proof. So my given statement is that C is the midpoint of B, E, and AD. That is given to us. And I'm going to mark what that means on the picture. It's not that this information is necessarily given. I can infer this information, but none of this information is given. I'm just going to mark it on the picture so I know it for later. Well, if it's the midpoint of BE, that means this segment is congruent to this segment. BC is congruent to EC, which is actually our second statement there. I also know that the same kind of thing is true here. AC is congruent to DC because it's also the midpoint of AD. So we could say that based on the definition of the midpoint, I'm going to say definition of a midpoint, we know that BC and EC are the same. And using the definition of a midpoint again, we're going to say the same thing except with these other two segments. We're going to say that AC is congruent to DC. Okay, so I'm trying to eventually prove that ABC is congruent to DEC. I want to show that these two triangles, this triangle and this triangle, are the same, using one of my 5 theorems. I'm actually just going to list those so I know what my options are. So those are my 5 options. If I can get to any one of those, then I can show that these triangles are congruent. Right now, I have a pair of sides here. This and this are the same. I have another pair of sides here and here. So I have 2 pairs of sides. So I have 2 pairs of sides. I have 2 pairs of sides, so I'm leaning towards one of those. I really don't have a way to show that this is congruent to this. I'm trying to get to side, 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 but I really don't know if AB is congruent to ED. So instead, I'm going to use vertical angles here. That angle and that angle, those are vertical angles. So they have to be congruent. So I'm going to say that BCA is congruent to DCE by the vertical angles theorem. Angle BCA is congruent to DCE because they are vertical angles. And now looking at this, I want to think about which theorem I'm using. I have a side, I have an angle, and I have a side. So by side, angle, side, I know that these two triangles are congruent. All right, looking at number 2. First, I want to think about what given information I have. So I know that this side is congruent to this side. This side is congruent to this one. That's the given information. LM is congruent to LO. MN is congruent to ON. And then my next statement is that LN is congruent to itself, which might seem silly to say. But it is the third side. That's really what we need. We have a side, and another side. That's really what we're trying to get to. We're going to say that LN is congruent to itself, and this is called the reflexive property. Again, it might seem silly that we're even saying that part, but we need to use one of those 5 theorems. We're using side, 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 so we need that last pair of sides. We have 2 pairs here just given to us. This is the last pair that must be congruent for us to use that theorem. And this is actually a really common thing. Anytime you have a shared side, that side is a part of this triangle, and it's a part of this triangle. So it's giving us that last pair of sides that we need. And that is called the reflexive property. Number 3, we're given that QS and RT are parallel. We have 2 parallel lines. We're also given that angle R and angle S are congruent. Here they're marked as right angles, but really the only given information, or at least the statement in this proof, is that these are congruent to each other. I'm going to mark them as congruent. All right, so our next statement that we're trying to get to is that 1 and 2 are congruent to each other. So angles 1 and 2, angle 1 and angle 2. Well, if these are parallel lines, and this is my transversal, those are alternate interior angles. So now I just want to think about what I have so far. I have this angle congruent to that angle. I have this angle congruent to that angle. And now my next statement is that QT is congruent to itself. This side is congruent to itself by the reflexive property. And the reason that really helps is because I have my 2 angles and now I have a side, which pretty much guarantees that I have congruent triangles. It depends on where that side is, but it's just going to change the name of the theorem. We have an angle We have the next angle over, and then we have the side that's not included. It's not in between those two angles, so we call that angle, angle, side. I'm going to skip around a little bit and have you come back to anything that I don't complete here. I'm going to do number 5. So my given information is that BC is congruent to DA. BC is congruent to DA. I'm going to mark that. And AC bisects BCD. AC splits this angle directly in half. All right, so based on that being a bisector, now I can say that these two angles are the same. It's part of the definition, so now I need to state the conclusion there. I need to say that BCA is congruent to DCA by the definition of an angle bisector. So now thinking about what I have a side, the next angle, and then I have this shared side, which is really where I'm heading. AC is congruent to itself by the reflexive property. And then these triangles are congruent because we have a side, another side, and then the included angle. Side, angle, side. The angle that we're using is squished in between those two sides. And you also want to be careful about how you write this. I mean, it's given to us here. This is what we're trying to prove, but the order really does matter. We're talking about triangle ABC, and that's congruent to triangle CDA. So the A matches up with the C. Those are corresponding parts in those triangles. All right, we're going to do one more quick bit together. We're going to go on to number 7. Here we know that AC is congruent to BC, and that M is the midpoint of AB. Now this next part that I'm going to mark is not a given. It's something that I'm going to have to show in one of these statements. But I do know that this is congruent to this because that's the midpoint. Actually, that's going to be the first thing I do. AM is congruent to BM by the definition of a midpoint. If I know that M is the midpoint, then I know I have those congruent segments. I also know that I have this segment that's congruent to itself. CM is congruent to CM by the reflexive property. Oops. And so those two triangles have to be congruent because I have all 3 sets of sides. ACM is congruent to BCM by side, side, side. I have all 3 sets of sides that are congruent, so the triangles have to be congruent. All right, use the rest as practice. If you need to rewatch the video, rewatch the video.